Okay, I think it's 5. Welcome once again to this talk by Ivan Utkin, who's from ETH Zurich, and he's talking about FastIce.jl. Over to you.
All right, thank you for introduction. And yes, I'm going to talk about how do we model ice flow using GPUs and Julia. So we are a small team of researchers scattered across Switzerland, but yeah, so mostly it's done together with my colleagues. All of them are here today. So yeah, a little bit of motivation. So why do we want to develop the code to model ice flows using GPUs on massively parallel on supercomputers? There are actually other codes that do model ice flows, but so the target of our study, the ultimate goal is to be able to resolve things that are called ice streams. So here you see the map view of Antarctic ice sheet, and colors are velocities. And you can see, so these two white circles, they show, well, what's called shelves. And on top of that, you can see that this shelves are fed by this very kind of narrow structures that are called ice streams. And there, the velocities of the ice surface, they reach kind of enormous values. So yeah, you can see there's a logarithmic scale, and in the kind of deep in the land and the ice sheets, the velocities are as low as several meters per year, and in this ice stream, they reach velocities for up to 3 kilometers per year. And so this is important because this is how most of the ice gets discharged from the ice sheet into the ice, eventually contributes into the sea level rise. So understanding the dynamics of the ice streams is important. Right, so yeah, these ice streams, they are fast-flowing corridors of ice, and their formation mechanisms, actually it remains unclear. So we know that they are linked to certain mechanisms, and there are some ideas, but still there is no kind of universal model that kind of would capture the formation, the onset and the shutdown of these ice streams, in a somewhat realistic geometry. And one of the problems is the problem is multiscale. First of all, right? So the ice sheet has the characteristic size of thousands of kilometers, and the length of the ice stream is 100 kilometers, and the shear margin, basically the kind of the narrow region where the strain rates are, the deformation is the highest. So this is the lowest scale that you need to resolve if you're trying to model this process numerically. It's few kilometers, and actually, if we start looking at the three-dimensional picture, then there could be some features that are like meters and tens of meters, and this problem is essentially three-dimensional. So to capture adequately all the scales, we need to be able to resolve them across all these spatial and temporal scales. Right, so there are some smaller examples that are kind of our toy models that we play with, and one example is this Vavilov ice cap, which is part of the Russian Arctic, and this is the first case of ice stream-like formation in the modern data record. So usually with Antarctic and Greenland, we can only look at this ice stream since they were there, since forever, and so we can only hypothesize what were the time scales and the dynamics and kind of the processes leading to the formation. And this small ice cap, so this is not an ice sheet, it's a much smaller object. And there the stable stream-like feature, so this kind of corridor of ice that formed just over over the course of a few months, which also kind of sheds some light on the characteristic timescale that has to be resolved. So how do we handle this problem? We handle it with supercomputing. So yeah, we're kind of making it our goal to be able to handle all the scales to capture this shear bands, so this narrow horizon of deformation. So yeah, so far kind of we managed to get some compute time on the largest supercomputer, which is powered by AMD GPUs, which is in contrast to well, all previous supercomputers that were well, harnessed in the NVIDIA GPU. So there were some kind of novel aspects that had to be well, handled. So FastIce.jl, it's well, it's a library, it's a package, and this is our ice flow model that we develop. And it solves what is called thermo-mechanically coupled Stokes equations. So you might have heard about Navier-Stokes, so which are, well, the system of equations that models the fluid, the dynamics of the fluid, and Stokes is actually the same as Navier-Stokes, but without some, well, inertia, basically, so neglecting the inertial effects. But yeah, we have this thermomechanically coupled, which thermomechanically means that temperature variations and the interactions between mechanics and energy balance are important, yeah, because when the ice deforms, it heats up, so by kind of friction, and this in turn lowers the viscosity, which kind of leads to some interesting feedback. One of them is, well, can be believed to be linked to the formation of these ice streams. So we need to solve it over irregular geometries to be able to study real objects. So all the algorithms are fully GPU accelerated. So, well, we use kernel abstractions.jl. So everything is actually backend abstracted, including GPUs. So, and not only the well, the kernels, but the algorithms themselves, they have to be carefully optimized and designed to fully utilize the power of GPUs. So which means that they have to be optimized for memory throughput and, well, and some other things like locality of the access. We try to avoid random memory access. And we try to minimize the extra memory needed for the solution as much as possible. So yeah, we use conservative finite difference discretization on regular Cartesian grids because this is the simplest way to, well, tick all the boxes that we need. Yeah, so we need conservative methods because we have sharp gradients of the fields, including temperature. So, and if the method is not conservative, like for example the standard continuous Galerkin finite elements, then there can be kind of some significant effects like loss of energy. And finite difference discretization, it's something that is very simple to implement on GPUs, and by default it will already give decent performance. Yeah, so if the grids are regular, that means that we don't need to store any kind of distributed structures. We can implicitly treat the parallelization and implementation. So yeah, instead we have to handle geometry, irregular geometry, and we do it with what is called immersed boundary method. So yeah, and this the solver, just kind of to advertise the bit, is part of the project that is called GPU for Geo. It is, well, it was recently finished but extended for 1 year, and yeah, the goal of the project is to develop some novel GPU multiphysics solvers. So yeah, here there's okay. So there's an example of localization. Yeah, here this thing, it should, yeah, it plays now. It will kind of slowly accelerate over time. So here you can see some artificial geometry. So what happens over time is that the flow, so this line kind of arrows, they show the velocity field, and these contours show the energy localization. And here on the right panel you can see the slice showing, I guess this is the temperature, so it shows that we have the localization and heating up of the well, the ice close to this bumpy rough features on the bedrock, so which is essentially what we try to resolve, but on a much larger scales. And the rest of the talk will be not about this, but about how we use Julia to implement well, all these things. So FastIce is, again, it's a library, so it's not a standalone, it's not a package, so it's not just an application that takes some configuration file and yeah, runs it. It is, well, tries to be Julia idiomatic, so it's a library where the configuration file is written as a Julia script itself. So it's structured like this. We have the FastIce library. It's just the solvers which implement the models. There are several of them, so isothermal, thermo-mechanically coupled. Well, also we have distinction between having this irregular geometry with immersed boundaries and not having, etc. So these are just the solvers. We have some tooling package. Well, right now if you search for it, you won't find it. But it exists. And finally, we have the core package. So this bottom panel is the core package, which recently, so this was what I was doing kind of this year, mostly at some point we realized that all these foundations and something that kind of helps developing this grid-based finite difference code can be nicely packaged and help us to develop some other experimental codes in general. So now it's a standalone package that's called shmi.jl. I will talk a little bit about it. And yeah, so it supports all these kind of things that make it possible to implement this model. So how do we handle grids? How do we handle, well, fields in mathematical sense, which can be discretized or continuous, differential operators, some interpolation, boundary conditions, distributed components, and some other things. So, well, some of that is a bit like transparent. That means that this is a work in progress, not implemented yet, but is being worked on. So the next part is, yeah, it's a little like the something that I'm excited about is the progression of the code. So how I was developing it over when we started, well, several years ago. It's just an example how this high-level abstractions in Julia help to develop more readable and easily maintainable code. For example, this is, well, one of the functions that we need in our solver. This is a function that computes stresses. And to compute stresses, well, there is a mathematical notation. You might not understand what it means, or most likely you do to some extent, but so this is just the set of equations. And how do we write it in the code? Of course, we want it to be as close as possible to this notation because it's readable, and well, also it helps new people to join and to contribute meaningfully sooner. And yeah, the first version, it was, well, you don't have to read this. It's obviously that it's just spaghetti code. It's completely unreadable. I cannot read it. I wrote it. And yeah, this is when I realized that we have to introduce these high-level abstractions. There was a high, like the activational barrier to overcome because I was afraid that if I make this kind of easily accessible high-level abstractions, it might not work on GPU, or it might work but be much slower, and so on and so forth. But I gave it a try, and yeah, early 2024 we have a somewhat better representation. So you can already guess that some of these things, they somewhat closely resemble the math, but there were some things that I was not happy about. And so the most important part is this check bounds. We need to check. We've used several kernel updates together to better utilize well, caching and the shared memory of the GPU, so that we read as few as possible things from the memory at the same time. And these check bounds, well, first of all, they look ugly, and second, they make the things a little bit slower, and in some cases, even not a little bit, but quite significantly slower, well, because of some extra machinery that GPU packages needs to do to make possible this check and bounds and report on the errors and throw in an exception from GPU, etc. So I wanted to get rid of that, and yeah, so finally, now with this foundational library, shmi.jl, the same kernel looks like this. So you can just kind of map basically every mathematical operation to its counterpart. This is how we compute it, and yeah, it's not exactly the same, but it's much, much closer. You don't have, yeah, you just have some kind of partial derivatives, some interpolations, etc., but it's very close to math. And what is more important is that this abstraction comes for free. So Julia does a very, so when you tell it to inline something, it will inline something, and it does it much more well willingly that, for example, some other packages that might refuse to do this. No matter how hard you try, without some intrinsics, it's difficult to do. But in Julia, everything gets inlined and generates the same LLVM code, or well, not LLVM probably, but the machine code is exactly the same as if you would write the spaghetti code by hand, which kind of makes me quite happy. So yeah, this is. It started originally as a core library for FastIce. It's what it does is that it simplifies the development of algorithms on regular grids in general, and yeah, it provides some tools that help you to deal with grids, differential operators, some boundary conditions, etc. Important, so kind of a novel thing is that it's not just backend agnostic. Many things in Julia are now backend agnostic, but it's also dimensionality, so it fully kind of utilizes the multi-dimensional programming in Julia. Initially, API was heavily inspired by Oceananigans.jl, which is a wonderful package. Yeah, kind of one of the reasons why I still decided to go with well, separate solution, because we have different needs. So we're also a CFD package, but not CFD in the same sense in Oceananigans. So yeah, I decided that it was just easier to implement what we need in a separate package. So here you can see this code snippet, what it looks like to use some of the features. We can create a grid. Well, here in that case, it's a uniform grid. It can be also non-uniform. We allocate some fields on a particular backend. In this case, it's a CPU. We initialize these values. And then we can, well, apply these boundary conditions. Yeah, so I won't discuss it in details, but there is this thing called batching. If we have multiple boundary conditions, they are batched together and sorted by dimension, by size, in well such a way that you only call one GPU kernel. So you don't pay for high-level abstractions in that case, at least. So yeah, the next thing that I wanted to show you quickly is the distributed part of FastIce. So we have algorithms that are very simple. We trade the algorithmic efficiency for well, basically very good scalability. We have much more iterations of our numerical code, so we recompute things redundantly all the time, and we have a lot of iterations, but instead all the operations are very local, and then it's very important to be able to hide the communication, the communication behind computations. So what it means is that basically, if you look here on the right side, so unfortunately I don't see my mouse, but yeah, so this bottom panel with this green lines is basically the execution on the GPU of a kernel on a GPU. And what you can see is that when so this top long green line, when it ends, the next one immediately starts. So, and usually if you don't hide this latency of communication, there would be a huge gap that would be just GPUs idle, waiting for communications to the MPI to exchange things over the network. And the standard way to do this is to use what is called non-blocking communication and to decompose the domain into inner and outer parts, where the outer part finishes first because it has a lower volume, and the inner part is the bulk of the computation, so this is this upper line. But when the outer part finishes first, so these are these yeah, you can see these shorter green lines below the long green line. These are the outer parts, and when it finishes, we can immediately start MPI communication without waiting on the bulk of the data to finish computing. And this is only achievable because we have local iterative methods. And then, yeah, as you can see, we don't have any gaps, so the MPI manages to exchange everything that it needs to exchange, while this long green line executes. So now, yeah, the question is, how do you program this? And the usual way, so if you do it in C, usually you would just, this MPI and well, in GPUs, they usually return you something that is called future promise, or some token that encapsulates the ongoing concurrent computation or communication, some I/O. And then you need to loop. So if you have many of these requests in MPI, if you know it, so this when you launch the receive and send, you get the request back, and then you need to loop over all of them to until the waits, and it also leads to spaghetti code. In Julia, recently all the packages they started to more and more leverage this cooperative multitasking capabilities. So they map the ordering of operations to the built-in Julia cooperative tasks model, and currently all the GPU backends support this. And MPI to a certain extent also supports this. It's not maybe there's not enough syntactic sugar, but you can work around this. And the snippet on the right, instead of just looping over these requests, we spawn several tasks for things that should execute concurrently, and within each of these tasks, we just write the code as if it were a serial code. So we untangle this long spaghetti structure and write much better looking codes. And on top of that, it helps a lot with interaction between packages. So if you have several things going on, you call some libraries that also do some I/O, as long as it is non-blocking and implements this cooperative multitasking things, which basically means that it cannot block. It needs to always return the control to the Julia scheduler. Then you will have this nice interaction. So we thought that it was interesting to try this high-level thing to see if the Julia runtime is efficient enough to run things on, hundreds and thousands of GPUs. So one question that you might have is, high-level features are not for free. Of course, they're not in many cases. So I was, showing you before that some of the features come for free, which is, a miracle somehow, but some of them are not actually for free. And when we first started playing with it, it was Julia 1.9, and we realized that if you just spawn a new task each time when you do the computation, which is very elegant and short code, but it leads to bad performance. So up the top panel is a CUDA-C implementation. This bluish lines, they come directly after one another. So this is the GPU execution, and CUDA.gl. If you have this multitasking, then you see this nasty gaps that that are comparable actually to the runtime of the of the code. So the takeaway is, of course, always profile your codes. Thankfully, Julia gives us tools for that. It means that making this API calls cooperative, it needs some caution. With Julia 1.10, the situation improved quite a lot, because the garbage collector became, so the culprit, why is that bad? Because when you create a new tasks, it allocates quite some information, and when the task finishes, garbage collector starts doing bad things occasionally, and it leads to bad performance ultimately. So here, thanks to Valentin Chiravi, he in 10 minutes he drafted the codes, and then later for 1 month I was trying to understand how it works and make it work. So essentially what we did is we switched from this short and very local tasks to what is called long-running tasks. It's somehow a blend in between this the old approach where you loop over things and the task-based approach when you allocate something. So it works like it's a worker. It's a struct that is a worker. It has a channel that accepts work. It does the work, and then it notifies an event that the work is done. And then each worker gets its own local state. And basically, if we want to, some things to execute independently of one another, we just submit it to different workers. And then, for example, you have one worker, it's the left side of your computational domain. Another worker is the right side of computational domain, and you submit two things to them, and then they get executed cooperatively, concurrently with one another. So, for example, one can weight on the GPU computation, while other is already started doing MPI. So it solves the issue of expensive finalizers almost. I will show you the benchmarks, and you will see what's the almost part. So yeah, a couple of words about GPU performance. Kernels in FastIce, they are memory bound. So we need to measure memory efficiency, how far we are from simply copying the memory around. We have, well, the metric, the standard metric for that is the effective memory throughput. Yeah, we reach about like 60% of the theoretical things of the peak memory throughputs with a Full-Stokes simulation in both 2D and 3D. So, which is not 100%, so we still pay some price, but we kind of, for now, we live with that. So next thing, so one thing is the one GPU performance, and the other thing is the weak scalability. Yeah, how good we perform compared to just having things on one GPU. We decompose the domain statically. We use MPI for communication between processes, and we achieve about like 95% of parallel efficiency compared to one GPU, both on, well, so the left panel is SpeedDyned, so NVIDIA GPUs, and right panel is Lumi, up to 512 nodes, and there we reach 96% of efficiency. Yeah, recently we managed to run the solver, the thermo-mechanical 3D Stokes solver, on a full machine. So yeah, they give us 6 hours just to test stuff, and we run it at effective resolution of 18,000 cube grid points. And yeah, so we were surprised to see that if you enable garbage collector, then it's actually, so with Julia 1.9, it would drop to 0 very quickly. Or, well, not to 0, but like to 1%. And still, many recent improvements, it's actually not too bad. It goes like to 92%, but still having GC on during the benchmark still negatively impacts performance, which means that we cannot, for now, get rid of these long-running tasks and disabling GC and kind of some optimizations. So yeah, this is practically what I wanted to show, and here are some next steps. So yeah, we had this GPU4Geo project, which was about writing these solvers, and there is well, some ecosystem around it, including all these kind of packages. You might know some of them, including parallel stencil, implicit global grid, which is, well, the kind of somehow the foundation of the thing, and well, Sam will I guess tell about it more in the future. And so what we submitted is the another project which is called DGPU4Geo, which is about, well, the same but for the reverse modeling to compute sensitivities. So yeah, if any of you will be a reviewer on this project, please say yes. Yeah, that's it. Thank you. Here are some links if you're interested in checking this out. Don't be surprised by very informative documentation. Just practically, yeah, not so good so far. Yeah.
Thank you, Ivan. That's great. We have time for a couple of questions, I think. Yes. Let me start at the back here.
Thank you, man. Thank you for the presentation. I have a question, actually 2 questions. The first one is, can you tweak the final difference order of accuracy? Like, I noticed that last year you guys were using parallel stencil, and in parallel stencil, I think you only can use second order accuracy. Can you guys like use 8th order or 10th order? Can you guys tweak that, or is it hard-coded?
Yeah, so, well, so in parallel stencil, it's mostly the backend abstraction. There are macros for finite differences, but well, you can implement everything with any order, but you will not have this macros.
Yeah.
And this chmi.gl is, well, an attempt to provide some extra things just to compute these derivatives. For now, it's only a second order finite differences. In ideas, well, the idea is that you can make this a parameter, the order of the approximation, but for now, and what we are using is the just the second order finite differences, which kind of, well, mostly because of locality of computation.
Can I ask another question? Yeah. And why did you guys decide to make a different implementation of the same basically principle from parallel stencil. Why did you guys switch to this new project?
Well, it's not a new. So so parallel stencil is backend abstraction, right? This to me it has nothing to do with backend abstraction. So it's just the functions that you can call within parallel stencil, within kernel abstractions, or within your menu loops. So it's everything that is not about backend abstractions. It's just like derivatives and gradient and stuff like that.
Hi, thanks for your talk. I have a quick question. So the work that you're dealing with is usually mostly finite differences, but within this chimie package, like I'm working with finite volumes for surfaces, something similar. Would it then be able to pick parts of the chimie packages and work with finite volumes? So, like such an extension, would it make sense, or would it require like a complete rewrite?
Well, so kind of the main idea of chimie is to work with regular grids, and the finite difference that we use are conservative finite differences, which well, they are just equivalents to finite volumes or one particular implementation of finite volumes. So, and we have functions like well, compute flux on the interface, for example, which will compute something that is located in between two grid cells. So it can be a bit challenging to do anything that is not rectangular grids. I would kind of see that it will take a lot of effort. So yeah, we don't plan to have like general finite volumes on kind of unstructured or hexagonal or dual grids, etc. But in a sense, it is finite volumes because it's conservative. So
Thank you.
There's a question there. I think that's the last one we will take.
Yeah, thanks a lot. It looks extremely exciting.
thanks.
My question would be, I mean, I arrived a bit late, so maybe you showed that at the beginning, but what's kind of the code that I would use as a user, for instance, let's say for the bumpy bed, or for, you know, how does it look like, the code to generate that result?
Yeah, that's a good question, because so we were mostly working on the internals. So the API that is exposed to user, for now it has, well, some like blank spaces that need to be filled. I can show you what it looks like. So currently there are, well, you are responsible for setting up mostly everything using this chimie package, and then you create a model within this FastIce, and then you just, well, you write your own time loop where you kind of then call this advanced time step function. In the future, when we understand how to better package it, we would do that. But yeah, this would also actually some feedback on how you would like to see that also would be kind of very welcome, because otherwise we do it only in a way how we would like to see it, and it would be cool if we can do it in a way that other people could use it as well. So.
Okay, thank you, Ivan.